carbon composite is a mechanically programmable material designed for bone formation and renewal. The composition is 67% carbon strands for strength and 33% PEKEKK matrix for toughness. The matrix locks the mechanical properties of the fiber in place. A carbon strand is strong. It has a diameter of 7 microns that curiously has the same side of an osteocyte. In a small rod we have 400,000 carbon strands, only in a 6 mm Ostapek rod. The carbon strand percentage and orientation control enables coLigne to tailor the strength and the stiffness of each implant according to what is required. Ostapek is not titanium. Ostapek is not PEKEKK, but the combination of two materials in one makes new properties possible. Where is Ostapek built? Ostapek finds its origins in Mr. Lange Sr.'s work with plastic and composites for ski boots. Ostapek is now made in Colorado in a composite lab under high pressure that freezes the long filaments in control orientation. Each panel that was made since 1994 is stored in Colorado. Each strip, each implant is checked and verified for void, waves, and any other defects that can affect the mechanical properties. Why do we want to do spine fusion? What are we looking for? Bone is not a static material. Bone is a living tissue, and so is fusion, which is a continuous process of creation, adaptation, and disruption of living cells. The osteocytes, the bone cell, act as sensors, and based on the inputs they receive, they decide whether they live or whether they die. Mechanobiology as a science has developed enormously in the last years. Already in 1970, Frost was the first one discussing the reaction of bone cells to too much or too little mechanical stimulation. In 2021, the Nobel Prize was shared by two mechanobiology scientists for discovering how cells feel and act upon physical stimulation. So both mechanics and biology have to be taken into account when we want to design a spine implant. What is the potential of Ostapek in this context? For cage design, the carbon strands are oriented like bone trabeculae. Strength is placed where required, and the rest is left open for bone graft to increase biological potential. For the longitudinal elements, carbon strands, quantity and orientation can be programmed to tailor implant strength and elasticity for the slight deformation that the bone tissue needs to form and reform. Ostapek is osteophilic, without a coating, to enhance early bone proliferation. What do we have? Today we have 130,000 patients treated with Ostapek implants. We have 29 years follow-up, 3 major markets such as Europe, United States and Canada, and 25 years of publications. What do we see in this experience? Tests show improved bone cellular density and viability on Ostapek compared to titanium surfaces. Carbon composite spine implants showed 5 times more cell growth compared to PEKEKK, according to multiple publications. On the carbon composite implant surfaces, human bone cells distribute continuously and homogeneously. On PEKEKK, however, bone cell clusters were found multi-layered and discontinuous. The carbon strand electroconductivity is thought to contribute in the bone formation process as well. When less rigid pedicle fixation constructs using Ostapek carbon composite rods were compared to the classic titanium constructs, the patients treated with Ostapek show a slightly faster fusion and an improved pain score and quality of life. What else does Ostapek bring. Ostapek is radiolucent, a key feature for tumor patients, both for radiological follow-up and for treatment. Patients live longer, so must the implant-to-bone construct. Fatigue resistance become a key factor. Some example of implants made of Ostapek. This is an Arriva cage made of Ostapek. It hosts a high volume of bone graft in these windows, and it offers the possibility for bone graft to adhere to the end plate. The cage becomes an extension of subchondral bone. The Trabe's corpectomy cage is another example of what is possible with Ostapek composite. The thin and slim walls for deformation and for space for bone for the maximum biological potential. The Ostapek VBR cages and construct associated posteriorly with either the Ostapek rod or titanium rod, if necessary, are used for the most critical tumor surgeries. The construct gives stability, the best possible interface with living tissue at the end plates, and the possibility to follow the patient with a radiological follow-up and treatment if necessary. The Ostapek rod, from one level, as in this case, can span also to more complex curvatures for multi-level surgery. Within the same geometry, the mechanical properties can be adapted and programmed from a standard to a less stiff configuration to enhance bone formation and stimulate the cells.